And as per popular request, he's going to tell us fractal calculus.
So yeah, so essentially what I'm going to do, like Clara said, it can be something like a tutorial. So what I'm basically doing is, so I can't remember, 2, 3 years ago, Arthur Eckert came to me. Okay, I mean, you know who I am from yesterday, I assume. Are there people who weren't here yesterday? Okay, so actually I'm going to repeat some stuff, so that's good. So yeah, my name is Bob. I'm a head scientist for Quantinuum. I was for a long time a professor at Oxford University. At some point in my life, very far away, I was actually here in the Mathematical Institute, a postdoc. I'm also a distinguished chair at the Perimeter Institute for Theoretical Physics. And 2, 3 years ago, so I'm going to talk about the X-calculus. 2, 3 years ago, Arthur Eckert came to me and said, yeah, on popular request, the students want the X-calculus in his quantum information course. Bob, can you teach me the X-calculus? It's okay. I'll do 2, 3 hours of lectures about it. And that's kind of what I'm going to do now, with a little bit more context. So yeah, so Arthur Eckert is now in maths in Oxford. He's not in physics anymore, after he left basically to Cambridge. So the X-calculus is something Ross Duncan, who was here yesterday in the audience, and myself came up with. Ross is now the head of Quantinuum here at Cambridge, based at Cambridge. And we came up with that in 2007, something like that. We wrote the first paper in a bus in Iran, of all places. And it took quite a while before the mainstream quantum computing community started to appreciate this thing. It took quite a long time, but now it's quite widespread. So, I mean, this is a paper by Peter Shor, who you may know from the factoring algorithm. So he's been teaching this in MIT, the X-calculus, since 2 years, I think. Again, popular request from the students. So they're using it for error correction, so it's quite widespread now in things like error correction. When you go to photonic quantum computing, which, for example, PsiQuantum is doing, and some companies in the UK, like Orca, and in France, like Wandela, they're all using this now as their main language, because the encoding of a qubit in photonics is quite complicated. And the sort of computational paradigm they use, and I'm going to explain this today, is measurement-based quantum computing. They don't run a circuit or anything like that. They compute by just measuring. And that's one thing I'm going to explain today, how such a computational model just based on observation can work. So that will be part of the thing. And historically, Ross and I came up with this thing called the X-calculus when we were looking at a problem in specifically measurement-based quantum computing. So that's kind of the historical origin of the whole thing. Okay, so the context, I mean, I'm going to repeat a little bit from yesterday for the people who were there yesterday, but I'll be quick. So the language of quantum goes back to John von Neumann, who published like the Hilbert space formalism in 1932 in his book Mathematische Grundlagen der Quantenmechanik. But then 3 years later, in a letter to Gerrit Birkhoff, the lattice theoretician, who's known for his book on lattice theory, of course, he said, I would like to make a confession which may seem immoral. I do not believe in Hilbert space no more. So then von Neumann came up with a number of new fields in mathematics, one called quantum logic, which was based on lattice theory and things like that. I mean, people are still using quantum logic in things like psychology and stuff like that. But as like a branch of physics, or it kind of completely vanished. There was like lots of people like Stone, lots of famous mathematicians worked on it, like Stone, and then there was a theorem by Piron initially, where you show that you can actually reconstruct the Hilbert space from your lattice theory and all of that. But it's totally gone from practical use anywhere in quantum physics. Like I said, except fields like psychology, it's actually still used. And then other fields, of course, I mean, named after von Neumann, like von Neumann algebras, as a part of operator algebras, and then the study of factors of von Neumann algebras, like what von Jones got his Fields Medal for. That all was driven by von Neumann trying to come up with a new quantum mechanical formalism after he denounced Hilbert space. But again, very few of them are now part of a typical quantum mechanical textbook. Schrödinger, so one of the things people know von Neumann from, and this goes from like pure mathematics to philosophy, is the idea that if you're going to understand quantum mechanics in a conceptual way, and we're going to build a new formalism of quantum mechanics, the things we should start with is quantum measurements. We need to understand quantum measurement because that's for von Neumann, the thing which distinguishes quantum mechanics the most from classical physics, in the sense that when you observe, you change the system. The system goes in a different state. I mean, this is called the collapse postulate or things like that, or von Neumann's projection postulate. So for him, this was the core of quantum mechanics. What changes when you observe, and for example, operator algebras, we've got a big specialist here in the audience, was based on the idea that you got these spaces of observables and you want to study them, and this was very much following von Neumann. But Schrödinger had a different idea, said the most important thing of quantum mechanics is what happens if you bring two systems together, which mathematically corresponds with the use of the tensor product to use composite systems. So that was von Neumann's idea. Schrödinger's idea. Von Neumann was much more influential. When you go to the philosophy department, everybody's talking about the measurement problem and things like that. Everybody's talking about measurement, nobody's talking about entanglement. Because that's von Neumann's influence. And so this idea of putting tensor product composite systems to the forefront was kind of never looked upon as serious. Now, does anybody here, I mean, you know about quantum logic. Do people here know about quantum logic? Or have ever heard about it, vaguely maybe. So this is the idea that you generalize propositional systems as described by Boolean algebras to non-distributive lattices and things like that, which of course comes at a cost. You don't have a deduction postulate and things like that in logic anymore. And then basically what von Neumann said is like we need to reconstruct quantum mechanics from this changed propositional view, this changed view on logic, that propositions have a different structure than we're used to. And then there was a whole community, so many people working on that, and then it basically broke down on the idea that people were of course trying to reconstruct the quantum, the tensor product from this new propositional structure, and there was no natural way to reconstruct the tensor product at this sort of conceptual level. And that's been the failure of that program of quantum logic, because people start to realize how important tensor product is when things like teleportation and this sort of quantum computational phenomena start to come up. And so then a bit later, okay, so this is Schrödinger, I mentioned this yesterday. This is about the statement that composite systems are the most important thing. And around 2004, Samson Abramsky, who's a famous computer scientist, he used to be at Oxford, now he's at UCL because of the Cambridge and Oxford rules that at 67 you get kicked out, which is illegal, by the way, in the UK. It's illegal that they kick out people at 67, but yeah, they do it in Oxford and Cambridge because they know nobody's going to go to court because it's too expensive. This is a thing which combines those two places. So anyway, Samson is now at UCL, University College London, because they were happy to take him. They were happy to take him in, even though he was 67 plus. He had his own fellowship. He was paying for himself, and still they kicked him out, which is a little bit absurd. Anyway, so in 2004, Samson and I came up with something that's now referred to as categorical quantum mechanics. So we used monoidal categories. Anybody here familiar with monoidal categories? Some of you, yeah. So we used monoidal categories because a monoidal category is really the most basic structure in which you got systems, processes, and composition of processes. That's really a monoidal category. If you look at it formally, it's a little bit more complicated because set theory comes in the way. And defining something like natural correspondence is quite complicated. That's why Eilenberg and MacLean initially invented category theory to formalize things like naturality. Like saying that A composed with B and then composed with C is the same as A composed with B composed with C is quite complicated, as it turns out, because of set theory doesn't like triples. You know, you have to say that a triple, you have to define what a triple is on the basis of combining a tuple and then another thing and saying that all possible ways you can do that are all the same. And that makes actually the definition of a monoidal category quite complicated if you look at it in the usual symbolic mathematics. So this paper, this is a seminal paper, like we got like some test of time award for it this year, but very few people can read it because of all this category theory. This is Roger Penrose from Oxford in maths. When Roger Penrose was an undergraduate student and he was studying general relativity, he had to learn, well, let me see, can I see? He had to, of course, work with this sort of symbols, like with subscripts and superscripts. And in his notes, he started to represent a thing like that, like Q with ABC as superscripts and FG as subscripts, as blobs with wires. So he represented them diagrammatically, And then the way you usually combine these things by contraction and all of that is just like plugging some of these boxes together. So that's what Penrose started to do as an undergraduate. I mean, I don't know the exact date of that, but it's maybe early 60s or something like that. But this only appeared in one paper of Penrose in an appendix, which was something about negative dimensional tensors or something like that. I can't remember the title. He had this somewhere in appendix. He never really used this in scientific papers, so for a long time this was obscure. But anyway, so I basically took this paper and then I just wrote it in terms of pictures instead of monoidal categories. So slightly provocatively, I call this kindergarten quantum mechanics, but that's essentially where we start to describe things like teleportation and quantum mechanical phenomena just using pictures, which was fully formal because of the correspondence between Penrose. So in the late 90s, two mathematicians, André Joyal and Ross Street, they showed that these Penrose diagrams are equivalent in the complicated sense to monoidal categories, symmetric monoidal categories essentially. And that's I mean, they did this for braided stuff. I'm not going to talk about anything braided here in this talk. So their papers was for braided stuff. But yeah, so essentially, it took a long time for people to simply accept that these pictures are actually as much mathematics as whatever you do like with your set theory or stuff like that. But I mean, they are. Now it's fully accepted. I mean, there's like Vodsky got a field medal for stuff like this, like Von Jones got a field medal for using a lot of pictures and stuff like that. So of course, it became sort of mainstream mathematics. By the way, I was talking about like quantum logic and things like that, and like the main name is there, Constantin Piron, coming out of the line of Neumann. So Von Jones was a PhD student of Constantin Piron initially. So he was working on quantum logic, and that's where he actually learned about operator algebras and things like that. And then, of course, he went on to do all his work in operator algebras. Right. Okay. 13 years later, after that first paper and after a lot of work, there is this book which is now colloquially referred to as the Dodo book. Does anybody know why this would be called the Dodo book and why there is even a Dodo? Huh? No, I mean, my office in Oxford. Well, I mean, yeah, cool. I mean, cool. Why not? No. My office in Oxford is basically 50 meters away from the Natural History Museum in Oxford, and that's the only place where they used to have like dodo material, like they had a feet and a head, a foot and a head of a dodo. And now it's not there anymore because they're trying to reconstruct the dodo. And so it is now somewhere in a laboratory with rich people who are trying to bring the dodo back. But that's where it used to be. And then, I mean, I remember it was a Saturday morning, and I'd been partying the night before, like I did yesterday, and I got a call from the department. Oh, Bob, the person who's supposed to sort of talk to the parents on the sort of an open day when the parents come to the university is ill. Can you replace them? I was sort of dodgy, and I went anyway. I started to talk about dodos and explain quantum mechanics with dodo, and that kind of stuck. And from then on, this became part of the course. That's why there is a dodo there. And it's full of cartoons. So the cartoons, I mean, I should have shown some pictures of them. The cartoons are drawn by Alex Kissinger, my co-author. And I basically told him, draw this, draw that, draw that. At some point, you have to buy the book to see it. Actually, that's a good advertising trick. But at some point, I told him, draw a spider dressed as a dodo dressed as a spider. And this was a joke, but he did it, and it's in the book. So if you want to see a dodo dressed as a spider, you have to buy this thing. Okay, 5 years later, Stefano Coggioso, who's a former Cambridge student, by the way. I think he was an undergraduate student and a master's student here. He did his PhD with me in Oxford. We wrote this book, which I, of course, mentioned yesterday, Picturing Quantum Processes, and the key about this book is you don't need to know any maths. I mean, the only thing you need to know is angles. You need to know what an angle is like, like 30 degrees, 90 degrees, stuff like that. Initially, and this is to present phases in quantum mechanics. Initially, we were actually not even using that. We were using phases of the moon instead of like phases as numbers. But then after like, I don't know, after 20 pages of Stefano doing phases of the moon, he stopped. It was too depressing. Anyway, so we did angles. And in the UK, you learn angles at the age of 7. So that's kind of okay. Anyway, so we did this experiment. I mentioned this yesterday. This is from The Guardian. I mean, a lot of people miss this because I think this was published like really, yeah, 16 December, like this, just before Christmas and stuff like that. So people not taking much notice of the news. And what we did, like I said, and these materials are going to be released soon, is we made videos of the book, of the entire book. I produced some exercises of the book. And then we basically asked kids about, yeah, like I said yesterday, like we did a call in the UK, we got 1,000 candidates, we randomly selected 60, we made them do the course. They were all going to get a certificate, but at the end, we made them do an Oxford University exam, translated in pictures, of course, and 50% of the kids got distinction, which is quite a bit higher than your typical level of distinction for a typical Oxford University postgraduate course. So these kids effectively outperformed postgraduate university students from Oxford. They effectively outperformed them. So the distribution of the marks was interesting. It was like you had like 3 bumps. You had like a bump close to 0 of those who did nothing. There was no reason for them not to do nothing because everybody got a certificate anyway. There was a bunch who just did nothing. And I mean, if you were there yesterday, they didn't know how to fuse 2 spiders. No, they didn't have a clue what this was even about. Okay, those got close to 0. Then you had those like around 50, 60. Those were the ones who actually worked properly, not like the outstanding students or something like that. And they had like 50, 60. And then you had a bunch around 80, 90, who were the ones who understood things really, really well. So it was really these 3 blocks of results we had. I mean, I showed these graphs yesterday. I mean, it's probably, so most of them didn't know anything about quantum mechanics. That's this red. They work like 1-2 hours a week, not much more typically. They all want to go in STEM research. And so one of the things which is not, and the schools didn't plan, one of the things which I thought was most important is we had some sort of open question at the end. And we asked, what did you think about the course? And the answer which occurred the most was, it was fun. No, it was interesting, it was fun, which is really important. And that actually will get people in line with this question into some STEM subject who typically wouldn't do that. Because it's fun. It's not interesting, it's fun, which is important. Yeah, lots of stuff is going on now. Actually, I have to take a car after I teach here, and I have to rush to Oxford to give my lecture to Ghana. In Ghana, they're now running this course in high school. And you probably know next year is the year of quantum. Did you know that? United Nations declared next year as the year of quantum, 2025. And so this was proposed by Ghana. And then so they're quite ahead with these sort of things. So in Greece, they're also teaching this stuff in undergraduate. They were the first, so they already translated the book and all that. Which is, and lots of stuff is happening. And this is another slide, so much more is happening. I've effectively got 3-4 people just busy with the outreach around this now, since the experiment was published in The Guardian. We don't even have a scientific paper out yet. But okay. So why is this important? I mean, for quantum, we need a workforce generation, and we can't just start at university level, because it's a different way of thinking. And one of the other interesting results we had here was that the 15-year-olds did much better than the 18-year-olds. Why would that be?
Know less.
They know less. They have less to unlearn. Effectively. So this is what I'm explaining now. So yesterday somebody was talking about the Greeks. I'm going to go do my Greek story too. So quantum pictures move away 2,500 years of scientific tradition. So what happened in physics is you had these 2 pre-Socratics, Heraclitus and Parmenides. So Parmenides said the world, we're always living in a static picture. So everything is a picture. And then what dynamics is in our physics theories is going from one picture to the next picture. So first you define the kinematics, which is the picture, and then the dynamics takes you from one picture to the next picture. And all our physics is set up like that. So it's all following Parmenides. So Heraclitus, the other guy's point of view is like we're constantly in a flux. We're constantly in a process. Everything is a process. There is no such thing as now. It's so Parmenides is being, Heraclitus is becoming. And like these pictures, as I will explain, they're much more about like the Heraclitus point of view. So then, okay, yeah. Okay, Democritus. Democritus said the way we understand the world is how things are made up. So we break things in parts. Physics, particle physics. We try to understand physics by understanding fundamental particles. We don't try to understand mathematics by understanding elements and set theory and stuff like that. We try to understand biology in terms of genes and things like that. So this has been driving, trying to understand the human body is doing anatomy, like chopping it open. Yeah? So this is how Western science has been driven for a long time, trying to understand things by how they are made up. Now, Leibniz said, I don't know, the way we understand things is by its relationship to other stuff. Like, how do we understand the human? By basically talking to the human and see what relationship you establish with the person, not by chopping them open in pieces, right? I mean, we would all end up in jail if we do that, and all be dead, by the way. And that was Leibniz's view, and I mean, Leibniz was mainly thinking about space-time, like we understand space and time by basically relationship to space-time points, rather than where the point is or describing where the point is. And of course, physics has conferred this, like people like Carlo Rovelli, they're promoting now this view on space-time and quantum gravity as relational. So it's quite, but also the pictures I'm going to show are very much relational. Carlo Rovelli agrees that this is really the mathematics of relational thinking that I'm going to show you. Okay, I already said that people need to get used to this at early age before being indoctrinated. That's what you just mentioned. They know too much by the time they're 18 to learn this stuff. And this was part of the problem which we had with the quantum information community. People had a hard time understanding this stuff, this picture, because they want to translate to what they know. And this translation is very difficult. It's a non-trivial mathematical endeavor to translate the pictures to what you would already know typically. And so in the big book, the Dodo book, we do a derivation of Hilbert space from the pictures, and there you can see the connections, and it's not trivial, it's non-trivial, it's not something straightforward. So it's generally a different way of thinking. Another reason why it's important to teach quantum to everybody is what we see now with AI is nobody knows what it's doing, and people make the decisions. Now, I just read that Elon Musk is going to be like in the government in the US, of all things. So it wasn't enough that these AI people are already running the world. Now they're effectively also going to run governments, and nobody knows nobody understands it. Like Hinton who got like the Nobel Prize this year for, was it physics or chemistry? Physics, huh? Physics. Wow. So he's afraid of his own creation. He's afraid of his own creation. So nobody understands what that stuff is doing. So it's good with quantum to teach people very early on and make them familiar with it. Anyway, and so like I said before, there's also an opportunity to make STEM education much more attractive. Okay. Okay, I'm going to skip this. This is what I've been saying before. Okay, let's start with the maths. Okay, blackboard. I love the fact that they still have blackboards. In Oxford, they threw them all away and made, with the excuse, yeah, chalk is bad for computers, as if this whiteboard pen stuff is not bad for anything. I mean, it's complete and utter mess. We're now stuck with all these blackboards. They killed all the blackboards with the whiteboards. They killed all the blackboards in Oxford. But we, in our building, Quantinuum building, all the walls are blackboards. So we have a lot of blackboards. So this is from my wall. So basically, I'm going to go back to the Schrödinger story. So we're going to think about systems or things of whatever you want as living in wires. They live in wires, like electricity wires or something like that. Things live in wires. And they move in wires. They're in constant flux in wires. So systems and things will be represented by just wires. And if you got multiple things, you write a few wires side by side. So I'm already smuggling the tensor product in here by just drawing a few wires side by side. That's where the tensor product comes in. The first thing which comes in is the tensor product, before we say anything. Having multiple things. And then, of course, then you've got boxes which can have multiple inputs and multiple outputs. And this is doing something to whatever lives in the wire. That's the way you want to think about this conceptually. I mean, if you know flow charts, it's very much like a flow chart. No, it's different. So basically, if you like monoidal categories, like the wires correspond to your objects or your identities on objects. The boxes are your morphisms. Putting wires side by side is the monoidal tensor. Okay, I'm showing this here in the slide. you have to think of between two wires as actually a tensor product sitting, which means these wires are not separate in practice. They will be connected in some way by entangled stuff flowing through it. But, and then this is like the Kronecker product. This is like the Kronecker product. Putting two, so think of this as a matrix and another matrix, and you're making the Kronecker product. That's what this is. We got special kind of boxes, like a state is a box without an input. So I give you something and then you can do stuff with it. That's a state, and we know this for a triangle. I'll show later why. And then there is this word effect, which is now quite popular in quantum computing. How do you call this? A state? No. This is not. This is an upside down state. It's the opposite. It's like a functional. You would think of this as a functional, in the usual way. It's something that acts on states and gives you a number. It's a destructive measurement branch, demolition measurement branch. But some people, I mean, in the quantum logic, they would call this a test or something like that, or a question, because that's really you ask something about a system. If you go, okay, here. So most of you know Dirac notation. Yeah. Okay, so if you take this like state here, you turn it a bit around, you chop some corners on, you get like a cat. If you take one of these, chop some, you get a bra, and if you plug them together, you get a bracket. So I mean, I was mentioning functional. So this is the analogy of these things with like how you would typically see it in Dirac notation.
So what do you call it? What you had written effect.
The effect.
And now you have a graph, but it has to be like one-dimensional. I can't like.
Oh no, it can be. Oh no, it can be. No, it can be anything. It can be anything. You see, it can have multiple wires even. I mean, at the moment, I'm not even talking about dimensionality. I'm just presenting.
Like if I think of it as a graph, then somehow I'm taking a trace with a rank 1 operator. Right?
Okay, yeah. So these things, because they're projecting on a number, they're like non-degenerate. They're the result of non-degenerate measurements.
It's a linear map to rank 1, like to
okay, so it is to a rank 1.
Yeah, in this case, I mean, you can have other stuff. You can have other stuff too, but in this case, yeah.
Okay.
It's so effectively, this is. I mean, concretely, this is a map from whatever goes in, like tensor product of a few systems to a complex number. No wire means like the one-dimensional vector space. So it's basically complex numbers seen as a vector space.
You're restricting which such maps you consider because you only contract with the rank 1.
No, I mean, all I'm saying here is there are special kind of boxes in my language. All the rest exists too. Anything else you'd find in quantum mechanics exists too. I'm just saying, what does it mean to have no output? So the space, the nothing space, which you don't draw, is the one-dimensional vector space or Hilbert space, if you want. And that's part of the reason that the translation is a little bit complicated, because a state is really a map from a complex number to a vector in some space. It's a map. Everything is a map. That makes the translation slightly non-trivial. It's not like a vector. It's really a map from a complex numbers to, and then the complex number 1 will be mapped on whatever vector you're trying to represent. But everything is a map. A number will be a map from complex numbers to complex numbers. I think I've got numbers on the next slide. So yeah, numbers are things without inputs and outputs, and because they're not constrained by an input or an output, they can just dance around each other. You can, and then, what is the number 1? How do you represent the number 1? Empty picture, nothing. The number 1 is nothing, because if you multiply something with 1, it doesn't change it. So it's an empty picture. Right, and okay, here I'm just composing a bunch of boxes together. So this is like a process with inputs and outputs. Here you don't have an input, this would be a state. Here you don't have an output. Oh no, this is a number. You got no input, no output. So you can compose these things. And that's basically all you can do. You can plug stuff together. And that's it. So you got a formulas in which you can plug stuff together. That's it. But it does encompass numbers I mean, you got, if you represent this like, if these are matrices and stuff like that, then this would be a number. This would be just a complex number, some sort. Okay, so the X notation for, so now the X calculus is basically what I was just talking about, but taking very special boxes, very well chosen boxes, and not many. That's the whole point. So the X notation for, so this is the notation. So we got two kinds of spiders. We call them green and red, and the only reason we picked these horrible colors, which are like the worst colors for colorblind people, is that when we came up with the thing, I just had a red and a green pen, and it stuck. Everybody kept using it, so okay, that's it. There's no more reason to pick these colors. In the Dodo book, we use white and gray, I think, so to be a little bit better for colorblind people. And Cambridge University Press charged way too much if it would have been a color book. So, so okay, so you got these two things. You got we call them spiders. They have a number of inputs and outputs. And concretely, I'm going to define what they are. You need to consider two bases. So we're talking qubits now, two-dimensional spaces. So this is one basis, 0, 1, plus minus. Are people familiar with this notation, 0, 1, and plus minus basis? Yeah. So this is what people call the Z basis. This is what people call the X basis in quantum computing. And so they're basically they are what's called mutually unbiased, because the inner product of a basis vector of 1 with each of the other basis vectors will always be equal. So they're not biased towards each other. So these are two mutually unbiased bases. So the green spider is basically defined as follows. You take the 0, 1 basis, and then you build this. You build this. In a way, this is like a very big Dirac delta. I'll give some examples later, which will make it more familiar. I'll leave it on. So basically, you just build this thing. So you take basis vector 0, you build this, you take this ket and bra, and then you take 1, and you take this ket and bra. And I'll give some examples which will give you the idea how it works. In the case of the red spider, you do the same for a different basis, for the plus minus basis. You do exactly the same. And you will understand this better through examples. I think I've got some examples here. Yeah. So this one, see, one input, two out. So we read this by convention, we read these things from bottom to top. That's basically a physics convention, you know. Physicists think of time going upward. When they draw light cones and stuff like that, time always goes upward. So that's the only reason we read these things upward. So this is one input and two outputs. Let's go back. So the input is ket. So you got 1, 0 here, 1, 0 here, the input. You got a single 1 here, and you got 2 zeros there, the output, and 2 1s there. So what does this operation do? It maps 0 to 0, 0. It maps 1 to 1, 1. So it copies the basis vectors. It copies the basis vector. This is just copying of the basis vector. Now, there is something in quantum computing, which is just a result in linear algebra, which is called the no-cloning theorem. So the no-cloning theorem tells you that if you got an operation, a linear map, which copies a number of vectors, then these vectors have to be orthogonal. So the only thing you can copy is the elements of a basis. So this is the operation which copies the 0 and the 1, and nothing else. This is the operation which copies the plus and the minus, and nothing else. So they are different. They are different. I mean, that's one thing I should have to demonstrate, that these two colors actually mean different things. They are different. This copies zeros and ones. This copies plus and minus. This operation would be like the deletion operation, or the are people familiar with coalgebra? Besides coalgebra, so algebra is where you take like two things, like two numbers, and you add them up, or you multiply them, or something like that. Coalgebra is where you take one thing and you produce two from it. So it's like upside down algebra. So algebra is like going from the top to the bottom. I could put A here and B, and what I get out is A plus B, or A times B. Coalgebra is the other way around. You stick something in and you get two things out. It's becoming very prominent in computer science, mathematics, and stuff like that, the idea of coalgebra. So these pictures are both algebra and coalgebra. Stuff goes in two directions, really. Anyway, so this is a copying operation, and this is the unit to this, what's called a comonoid. So a monoid is a thing where you got two things in and one thing out. A comonoid is a thing where you got one thing in and two things out. And then this, and then you got things like co-associativity and co-commutativity. You can just, all the usual operations of a monoid, you can just stick co in front, and it's the same thing upside down. Huh? So this is like a commanoid, and this would be the co-unit of the commanoid. So if you stick something in here, and you stick that one out there, then basically this would become the identity. That's the idea. Why? I'll show you later. This is because of the rules we're going to introduce. So this literally is the identity. This is 0, 0 plus 1, 1, or plus, 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 minus, minus, which is just the identity. And they're the same, so we don't have to write the dot anymore. Because it's this is 0, 0. Okay, let's go back. This is state 0, 0, two system state 0, 0, plus 1, 1, the Bell state. This is the Bell state. 0, 0 plus 1, 1 is the same as plus, 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 minus, minus. So these two are the same. So again, we don't write the dot. Again, we don't write the dot because they're the same. Oh, what happened here? Uh-oh. Okay. Oh yeah, maybe I should have put electricity. Oh, come on. Are you back? Wow, that's cool. Okay. Wow. Okay. Okay, so we got the copies, we got the identity, we got the cups. They call these cups and caps. And the reason I went for Cambridge University Press and not Oxford University Press is because Cambridge University Press is CUP, cup. It's as stupid as that. I thought it was a good idea. That's why I went to Cambridge. Okay, can anybody guess what this is? I mean, I'm going back to the definitions. So this is dot with three things out. Oh, sorry. Oh, come on. So what do we have here? So we only have a state. We only have a state. So this part doesn't exist, and this part doesn't exist. So we got 0, 0, 0 plus 1, 1, 1, because we got 3, which is G at Z state. Yeah, this is the G at Z state, this one. G at Z state, pretty much what Zeilinger got the Nobel Prize for before this one. Huh? That's really that. Okay, so now to make things interesting, and because we want to turn this into a universal language for quantum computing, meaning that every matrix you can write, we want to be able to write this using these spiders. And you're not going to get there with just these sort of things. You need to add something which is called phases. So we're going to decorate the spider, and this really just means that you stick a phase there. And this is where the kids had to know angles for. Because this would typically be the angles you decorate spiders with. And I mean, we try to do it with phases of the moon, which in principle you can, but it's just horrible to draw. So we put some numbers in there. And then, so we call them phase spiders. And then, okay, that one. And you do the same in the other color. And that's all we're going to use. We're not going to use anything more. So some more examples. I'll let you show. Maybe I should go back a little bit. We stick these phases, and now you start to get an expressive language. So this, like, which would be the identity if there wouldn't be a phase, is really just what's called a phase gate in quantum computing. It's a matrix where all the off diagonals are 0, and on the diagonal you got a 1 and e to the I alpha. That's this. This is a NOT gate. If you stick a pi on the red one, you actually get a NOT gate. So that's off diagonals are 1, diagonally 0. It basically negates your basis vectors. And then one of the most coolest things is if you take green spider and red spider, and this is actually without phases, and you stick them together like this, or you stick them together like this, which turns out to be the same thing. So we draw it like that, is a C-NOT gate. So you're starting to get all the fundamental gates in quantum computing like this. So this, just the green and red spider together is a C-NOT gate. I mean, you remember the copying. So basically, this is the 0 vector, this is the 1 vector, and this is the plus vector, and this is the minus vector. Because these were the basis vectors which were copied by our copying operation. So these are sort of the fundamental elements you typically would need if you do quantum computing with these spiders. Yeah? That means 0. 0 angle, 0 angle. Uh,
The other one was like a sum over both basis vectors.
yeah.
That was
Or it's because a big
a few
circle
dots,
versus
right?
like a little dot. Is that the idea?
Wait, let me. So you're talking about these.
Yeah.
So these are states. These are states. They have no input. Wait. Yeah, the size of the dots doesn't matter. That's just me being clumsy. Yes, yes, yes. So the yes, yes. So the circle without anything is the same as this dot. That's a circle with a 0 or a circle with nothing is exactly the same as these dots. Yes. Yeah. Good remark. Yes.
No, that's not what I was saying.
Oh.
Did you just, yeah. So like if you label one with 0 or nothing and you label the other with 5, that's each of your basis vectors?
Yes.
So that's 0, ket 0 and ket 1.
This is ket 0 and ket 1.
But then the red dot with nothing, just the red dot with a line coming out of it, is that not a
That's this one. That's this one.
That's not a
This is the same as this one would be the same as a red dot with a line coming out.
red dot with a line coming out was a superposition of two things.
Well, it depends in which basis you look. It depends in which basis you look, of course. Yes.
Okay.
It depends in which basis you look, whether it's a superposition is not an absolute thing. It's a basis dependent thing. So whatever is superposition in one basis won't be a superposition in the other basis. Okay. Yeah, makes sense? So yeah, I mean, they're all superpositions. They're all superpositions if you look at them in the basis in which they are superpositions. It's as simple like that. Huh? Right. So this is sort of your general ZX diagram, the most general thing. And so there's nothing else you can do. Then just draw some web of spiders like this. Now let's do some maths. We're going to show some theorem. We're actually going to vaguely prove it even. I'm going to talk about universality of ZX notation. Theorem, any linear map between qubits can be written as spiders. So whatever you come up with, whatever matrix you give me, whatever linear map you give me between qubits, can be written as spiders. As a comment, I'm presenting today everything about qubits, but you can do this in all dimensions. It's just, I mean, the number 2 is such a degenerate number that everything becomes simpler. If you go to 3, things will become a little bit more involved because of the degeneracy of the number 2. 2 plus 2 is equal to 2 times 2 is equal to 2 to the power 2. So it's a very degenerate number. This is not true anymore for 3. Anyway, so let me prove this, and I'm actually going to rely to prove this on a standard result of quantum computing. Like one of the standard results of quantum computing is that if you got phase gates, like these guys, and you got C0 gate, you can build any unitary. That's some sort of standard result of quantum computing. That's why this is like a sufficient gate set. So you can build any quantum program just using, I mean, there's other representations, but this definitely does it, like the phases and the C0 gates, and we've got them. So we can build any unitary. Now we apply this to, say, 0 cats. So we can build any state. Because we can build any unitary, we can build any state. Because for each state, there is some unitary that takes you from 0, 0, 0 to that state. So we can build any state, and then we use our caps to turn any state. We take a number of inputs, and this is Choi-Jamalkovsky, if you know the name. People are familiar with the name Choi-Jamalkovsky? This is literally Choi-Jamalkovsky for pure maps. You take any state, and then you turn some of the outputs basically into inputs, and that's how you get any linear map. So I just showed that because of the fact that in this notation we got C0 gate and phases, we can basically represent any linear maps anyway. Yeah, okay. So far we've been purely descriptive. We've been just writing things down. We haven't done any calculations or computations with this stuff. Now calculations and computations come in by rules for spiders. And I mean, they will be simple, otherwise this would be a complete waste of time to even do this stuff. So the first rule, and this is all thanks to the definition, is that if you got 2 spiders, they just fuse together. You can check this from the definition, they fuse together. So any network of spiders of the same color is actually just a single spider. They just fuse together. The mathematical name Are there people here doing quantum algebra, quantum groups? So you know, so the mathematical name of this, and that's why we call it spiders, is a special dagger commutative Frobenius algebra. If you're familiar with like Frobenius algebras, which is like a monoid and a commanoid and some relation, so these guys are an example of that. But then on top of that, they're called special. I mean, some people have different names for these things. In different books, in different contexts, you find different names for the same thing. They're dagger, which means like, if you flip them upside down, it's like taking the adjoint, and this is okay. So there is a theorem which was proven by Jamie Vickery. I don't know, but did Jamie Vickery ever show up for this week? Because he used to be very much in this sort of theorem proved by Jamie Vickery and Dushko Pavlov, a picture myself, is that this equation for the spiders is enough to. So think of this as just an abstract structure, an abstract structure in a monoidal category, which is something about how you compose things. You got a family of things, and if you compose them, you plug them together, you get another thing of the family. You always stay in the family. That condition, that equation alone, interpreted in the category, in the monoidal category of Hilbert spaces and linear map and with linear product, guarantees you that the form of the spiders is always something like this. Something like this, okay. They're always defined by this expression on some basis. For some basis. So basically there is a one-to-one correspondence between orthonormal bases on a space and the kind of spiders you can have. They're the same thing. So this is a definition, where is it? This effectively is a definition of an orthonormal basis. It doesn't look like, there's no notion of sum here, there's no notion of scalar multiples, but this is equivalent to a definition of an orthonormal basis. And this already starts to push us in the direction of what I was talking about, of moving from Von to Schrödinger. That Schrödinger said it's composition the most fundamental thing. So this is the definition of an orthonormal base only using the language of tensor product and nothing else. You don't use sums, you don't use the notion of scalar multiple, you just use composition, using tensor product and composition of maps. And you can define an orthonormal basis in that way. So you already start, since you know like non-degenerate observables in quantum mechanics, they correspond to orthonormal bases. So you kind of see the notion of basis already emerging here. So when you see one of these spider families, you have to think basis, orthonormal basis. So we have two colors, which means we have two orthonormal bases. I'm now going from the concrete to the abstract. So when you see one of them, and you got your quantum mechanical head on, you already maybe start to think about measurement. Huh? At the moment, I'm completely ignoring normalization and everything like that. I can make a comment about it later, but typically when we compute with these things, we ignore numbers and factors like that. And at the end of the computation, because at the end of the computation, you can figure them out very easily. So there's no point like carrying them. Of course, if you're computing a number, you have to do that. If you want to compute a probability, you have to care about it. We'll see this later. We'll see something about this later. Anyway, the same is true for the other spider. So, so in this particular equation, there is no number to normalize. This is just true on the nose. This equation is true. We're going to see some equations later which are not true on the nose, where you actually need a number, but I'm not going to write it. Just to keep things simple. And here is one example. So here is one example. If you combine a green spider and a red spider, and they are connected by two wires, and this is important, two, not one, not three, two. They're connected by two wires, then these two wires go away. So I was telling earlier that this defines an orthonormal basis, this defines an orthonormal basis. Basically, what this equation concretely defines is that these two bases are mutually unbiased. They're as far apart as they can be from each other. So this is generally valid for all bases. not just qubits or anything like that. This means these two bases are mutually unbiased. This equation has a number, which I'm not writing. There should be like a thing without inputs and outputs on the right-hand side, which I'm not writing. But in principle, it should be there. And you'll see this arising in a computation later. So this is, of course, is a simpler expression of the same. Here, rather than a spider, I've just got a monoid and a comonoid. And it's a simple calculation to check that this really means mutually unbiasedness. And rather than showing this mathematically, we'll later see the physical intuition behind that, of this being mutually unbiased. Let me look at the timeline. Okay, let's do a calculation. I mean, I showed this one yesterday. So the rules to remember are same color fuse, different color, two wires in the middle, they go away. So here is calculation. First thing we do is, okay, we see a bunch of green spiders connected. So this, let me remind again. So we've got 3 qubits here. We've got 1, 2, 3, and we've got 3 CNOT gates acting on them. Here is CNOT gate, there is CNOT gate, there is CNOT gate. So it's a quantum circuit. It's a quantum circuit. We want to simplify this. I think last year people came up with a set of equations, like all equations you can have between CNOT gate and phase gates, that basically define all other equations. Some people came up with that, but it's just impossible to use that. It's just way too complicated in the equation. So now in this case with Z calculus, what you do is like you forget about the fact that this CNOT gate is a monolithic thing. It's one thing. We think about it as being 2 things connected to each other. Thinking like that, you can say, okay, we got all these green dots here, we got these red dots, and we can just fuse them. Because that's what we do with spiders. And now we got 2 wires between these, so we just throw them away. And like just 1 input, 1 output, red dot is actually just a wire. So we simplify this. And as I mentioned yesterday, this is part of state of the art on how you simplify quantum circuits today. This is how you do it with this method. There's nothing better. I mean, you can throw some AI at it, which people are doing to basically make it better. So now people are using this to get combined with AI, simplify quantum circuits.
So is the result you just mentioned from last year, where they had all the relations, that relations that you cannot get from?
Oh, these you can get all of them. From these you can get all of them. It's just that these rules are much simpler than all these relations you need to write down. If you don't break your CNOT gate in 2 pieces, then it's a humongous set of rules which are completely impossible to manipulate. But I mean, people didn't even know that you could come up with them. But last year it turns out they came up with something like that, some people. This is much older, this is much older.
You have numbers in the phases?
So yes. So okay, I think I'm going to show this next, I think. Oh, no, not yet. So yeah, the phases, they will just add up. They will just add up. And in this case, we'll see examples of calculations later. In this case, suppose that there is a phase here, you just move it out. There's a phase there, you just move it out. And you can just apply your rule. So yeah, they still all hold. So there is, okay, so for this rule is not the end of the story for 2 colors. There is actually a rule, so this means mutually unbiasedness. There's actually a rule which is much stronger than this one. And that's the one you actually need to, let me give it away, to compute everything you can compute. Effectively, like I don't want to give away too much for the dramatic effect. So those people who work in quantum groups and things like that, and algebras, they know this. This is a bialgebra. Well, not really, because otherwise I should put this one upside down, or this one upside down, I guess, to get something which people refer to as a bialgebra. Huh? This is bialgebra. And do people know Hopf algebras? So if you take these rules, and this, then you got a Hopf algebra with trivial antipodes. But this is not just, this is actually quite different from this for reasons I can explain, I'll show later. But yeah, if you're familiar with quantum groups and all of that, you will recognize this. So as it turns out, so this is the equation we really need. Now, and this is how mathematicians usually would write it, like this. So basically you got a comonoid here, you got 2 comonoids, like this, one input, two outputs. You got a monoid there, two inputs, one output, and they commute through each other. They basically commute through each other. That's what this is saying. And here, this is quite similar. It's the unit gets copied through, and this unit gets copied through. I mean, that's something we know from a while, just by how we constructed these things. Now, the reason I prefer to write this one instead is like this. So we're working with these nets of spiders. And what this rule, well, let me go. What this rule is telling me is if I've got a 2 cycle, which is a cycle with 2 dots, I can get rid of it. Yeah? 2 cycle is gone. What do I do if I've got a 4 cycle? I can't use this. So that's when this one kicks in. Suppose I've got a 4 cycle, then basically what I can do is I'm just going to label these 4 outputs. I'm just going to draw them here again. And whatever is connected to red, so 4 is connected to red, 2 is connected to red, we actually connect to green. Whatever is connected to green, we connect to red. And then we connect the 2, but my 4 cycle is gone. So this is a way to reduce your 4 cycles. As it turns out, and then what about 6 cycles? Doesn't matter. You don't need a rule for that. 8 cycles, you don't need a rule for that. Turns out this is good enough, this is all you need. You don't need anything more. Okay, now why, for those people who know Hopf algebras, I'm now just going to break the illusion that this may actually be closely connected, because it's not. So here you see, you have this equation here, the 2 cycle one, and this equation, the 2 cycle one, actually follows from the 4 cycle one. So in this language, when you got a bialgebra, it's automatically a Hopf algebra for free. And that's because of the spider fusion stuff. Because in the presence of the spider fusions, a bialgebra becomes a Hopf algebra automatically. So that's why it's quite different in spirit from your typical bialgebras. And let's show this. And the numbers will come in now. This is like a very enlightening equation. So, okay, you got this 2 cycle. We can turn this 2 cycle into 4 cycle by just pulling out these 2 things. This is unfusing. We unfuse these. We introduce a red dot here, we introduce a green dot, and then we unfuse them. Make sense? Yeah, we just unfuse them. Then we pull them out here, now we got a 4 cycles. So we can apply my rule. I mean, you can go to the ends and see how I connect them, and then you will end up with this. Now I've got a red dot here and a green dot. This red dot will be copied by the green dot. The green dot will be copied by the red dot. Okay, you see here are these copying equations. Red dot is copying green, green dot is, so these things get copied. See, now we have to be careful. This red dot is copied through this green, so one goes there and one goes in the middle. Green dot is copied by the red, one goes there, one goes to the middle, so we got this number in the middle. But we're ignoring numbers. But you see here why their numbers will occur. Scalar multiples will occur. In this calculation, I'm just ignoring them here. And it actually basically shows, yeah, somewhere there needs to be a correction factor. Otherwise, it couldn't be true. But we kind of ignore them most of the time. And you see, okay, then we got this and this, so this becomes this. So we derived the 2 cycle reduction from the 4 cycle reduction. Yeah?
Is it important in this picture to keep track of words like spaces and null spaces?
No, you completely ignore that. That's the whole point. You completely forget about all of that. You treat it just as a graph. Of course, you need to remember at the end that, okay, I treat this as an input, and this corresponds to this, and I treat this as an output, and this corresponds to this, but everything that happens in the middle, you don't care. That's the whole point. It makes things so much simpler than having to worry about that. Crossings don't mean anything. This is equal to this. So,
but it still needs to be crossed.
I mean, otherwise I couldn't. I mean, this is just okay. Okay. So this. I mean, this thing is actually happening in 4 dimensions, because in 4 dimensions there are no knots, there are no crossings. In 4 dimensions, everything moves through each other. So technically, this is in 4 dimensions, but I don't have a 4-dimensional presentation. This is literally it. So in 4 dimensions, there is no knots. Everything moves through each other. So technically, this is all happening in 4 dimensions. But it's because I have to draw it on a piece of paper that I have no choice to make things cross. I have no other choice. And it's because I'm writing it on a piece of paper. But these things can live in a higher dimension.
But where I kind of take them, like this middle one, it's not the same as where untwist them. Kind of like
But how can I untwist them? I mean, I cannot twist them.
Green, I guess, well, the green, I move it down, and the red, I move it up. Then there is no crossing of those wires. Can I do that, or I can't?
Yeah, you can just fuse them together. The crossing is something you can completely ignore. It's just an artifact of drawing things on a piece of paper. Effectively. Like for example, you see there is a, look at this, there is a crosses. I just untwist it. It has no meaning, it has no meaning. It just happens to be that on a piece of paper they have to cross to draw this.
Can you go one slide forward?
Further?
Yeah, here. Like, so why is this 2 and 3, those lines, they are crossed? Like, why didn't you draw them without the crossing?
I mean, I could have put a crossing on this side. I could have put a crossing on this side. I mean, one way or another, there has to be a crossing somewhere.
Oh, because you want to preserve the numbers going in.
Yeah. It's the rule. It's the rule. One way or another, I mean, I could have put the crossing here.
Yeah.
I could have put it somewhere else, like, but there's no way to draw this without a crossing. Or, well, maybe I could have like taken this and drew it there or something, which, so, yeah, but it doesn't mean anything. I mean, there is, of course, there are these things called braided monoidal categories and knot theory and stuff like that. And then these crosses are very significant. And then this is not equal to that. Yeah. I actually remember the first time I was in this room, I think Luke Kaufman was giving a talk here somewhere in 2004, 2005. So Kaufman from the Kaufman bracket in knot theory. I think that's the first time I was in this room, yeah.
You made a point of saying, like, you automatically get a Hopf algebra, so it's not like just a phi algebra, it's something more.
Yeah, I mean, that's the proof I just showed, huh?
Right. So,
that's this.
So Ross Duncan has a paper from a few years ago about these like Hopf-Frobenius algebras.
Yeah, that's where people start to understand all these things and how they're related.
And so that's like, this is an example of that.
This is like a very general example because you don't have an antipode. I mean, identity is the antipode. If you go to higher dimensions, it becomes less trivial. But yeah, so Ross has a paper, and then I think Pavel Sobocinski, I mean, there's two papers. One is blah, 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 Frobenius algebras are Hopf, and blah, 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 Hopf algebras are Frobenius. I think there are two papers like that. One by Ross and one by, I think, Pavel Sobocinski. I mean, for a long time, people like when we submitted first the first DX calculus paper to communications in mathematical physics, we got like this response: "Oh, we know all of that stuff already. That's just blah 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 blah," and we got rejected. And this went on for a while. That we got these sort of very negative reports from people from the field of quantum algebra until Sean Majid started to work on this, and people said, "Okay, so this must be something different because Sean is now working on this," and then that community started to realize, okay, this is actually quite different. And then a lot of people in computer science start to use this just not for quantum, to study like process algebras and things like that, and concurrency. So there's like a big activity now in computer science using the same, they don't have phases, using the same structures to study stuff in semantics. Yeah. Yeah, I mean, that's how we read these physical processes usually, yes. Of course, yeah, of course. It doesn't matter. So the word dagger, when I use the word dagger, it means everything you can just, it's like taking the adjoint of the whole thing, which is of course reversible. You can take adjoint and then adjoint again. Okay, like somebody asked earlier, if you got phases, they just add up. They just add up. Two colors. And wait, let me go on. For people who care about the Hadamard gate, you can just write down the Hadamard gate using phases. This is just the Euler angle decomposition of the Hadamard gate, so you can use that. It's part of the formalism. And you may want to make it explicit because it's a pretty cool thing. When you then take a green spider, you sandwich it with Hadamard gates, it becomes red. So Hadamard is like color changer. And it's handy to have it around for certain things. And it's like the color changer or so. For example, if I've got a Hadamard there, I can just push it to this green one, it becomes red, and it shows up in all the other legs. So this is a handy rule. You don't. It's not a generating rule, but it's handy to have it around. Okay, completeness of the X calculus. So completeness is a logical notion. completeness of an axiomatization of a model means you can use your axiomatization to prove everything you can, which is true about the model. That's called completeness. So there is a rule which we never use in practice, but there is a way in which you can basically, if you got green face, red face, green face on one wire, on a single wire, that you can swap the colors. There is a rule that you can do that. We never use it for anything, but it exists. It's true. And the reason I'm writing it down is because of the following theorem. All the rules I've shown before, any equation that holds for linear maps between qubits can also be derived in the ZX calculus from the rules I've given you. Anything you can prove using linear algebra, linear maps, using all of that, you can prove using the rules I showed you. And for that theorem, you need this rule. For any practical use, you don't need it. But for the theorem, you need it. I mean, this thing is something that neither Ross nor I thought it would ever be true. It was proved in like 2018 or 2019, I think, that effectively you can derive anything you can derive. Any equation in linear algebra can be derived in ZX calculus. And that's called completeness. Yeah?
These generalized diagrams with phases, is this specific to qubits? Or?
I mean, if you go, I mean, ZX calculus has, and all these completeness theorems holds in any dimension. We have this thing done in any dimension. Today I'm just talking about phases. I mean, this, for example, would be quite different in a higher dimension. This is a geometric property of a qubit that using this tree, using a z rotation, an x rotation, and z rotation, you can do any rotation. It's a geometric property. That's a geometric property of a qubit. Typically, your phases will consist of two numbers in higher dimensions, in 3 dimensions, or 4 in 4 dimensions. But all of this stuff can be generalized. So I'm not presenting this here, but this can all be done. Although this like completeness in all dimensions is only like 2 years old or something as a result. It's all quite new stuff. It's all quite new stuff. I mean, the most modern version of all of this is actually 3 spiders. Red, green, and then something else. And as it turns out, the something else corresponds to what people call the W state. Anybody hear about W state? So the W, if you throw in the W state in the mix, you get a formalism in which you can integrate, differentiate, exponentiate, and do analysis. I mean, I'm not going to talk about this today, but you can find papers about that. So yeah, I mean, I mean, should we take a break or something? Because I think we're over an hour.
Maybe.
Yeah? Okay, break.
That's just a state. You should be able to produce it. It's just this.
I mean, it's W state, like the GHZ state, is a dot with 3 lines. I can put the wires wherever I want. I can put them at the bottom. I can. Oh, you can. No, you can represent the W state in this formalism, but it's much more convenient if you take it as a primitive. Of course, you can actually I remember W state is like a triangle of green spiders with pi over 6 faces on the edges or something like that. If you write it here, but it's much more convenient to have it as a primitive. Why? You have to think about these dots as multiplications. They're like multiplications. And the W state is actually addition. So you're bringing in addition, and that's how you can then differentiate and stuff like that. You're bringing in additive content. Okay, so we're going to do some stuff now. So far we've only been describing. We already saw this one earlier. Huh? So basically you got these 3 CNOT gates, they fuse, these dots here, and the 2 go away, and that's how you simplify a circuit. So that was a very simple example. Now we're going to use this. This is essential actually also to do circuit stuff. Okay, so this is a typical example you find in any like Nielsen, Chang, or whatever textbook. Like you got these 3 alternating CNOT gates. Your 2-cycle rule can't do anything anymore here. So basically, we have to look for a square. I mean, there's 2 squares here. There's a square here. There's a square here. Doesn't matter which one you take. Okay, we take this square, and I label this sides 1, 2, 3, 4. You see 1, 2, 3, 4 here. Whatever's connected to a red dot will be connected to a green dot. So 4 is really connected to a red dot, so will become connected to a green dot. 2 is connected to a red dot, so will be connected to a green dot. 1 is connected to a green dot, so will be connected to a red dot. 3 is connected to a green dot, will be connected to a red dot. And I connect these 2. And then you see now I can basically fuse this green and this red. So the swap remains. The swap remains. These 2 will vanish. So basically these 3 are a swap. I mean, if you want to do this with like equations for CNOT gates, so this should just be a primitive equation. There's no way around it. This equation needs to be part of your set of equations to even start in itself. So, right. So now reminding you that this is 0 and 1. This is plus and minus. So, and I remind you the copying thing. So it turns out that, oh, sorry. So you got this basis vector, and so 0 is copied by the green dot, because the green dot was based on the green basis vector. This one is the plus, will be copied by the red dot, because the red is based on the plus minus vector. It turns out, and this is derivable, that the same is true for the other ones. I mean, this is true by constructance, but you can also derive it in the calculus, because you can derive any equation in the calculus. So I'm just keeping them in mind, because I want to actually show now, that the CNOT gate is a CNOT gate. Of course, you can prove this by just taking the definition of the of the spiders in Bayes, and you can concretely calculate it, but you can also calculate this in the calculus. So here is, oh, sorry. So what we're going to do is we're going to take a CNOT gate and see what happens if I stick a red dot here. If I stick a red dot here, it just gets copied through. This fuses, so I get identity, which means if in the control of my CNOT I put 0, it does nothing. On the other hand, oh, yeah, you can still see this, right? If in the control of the CNOT I stick a pi, the pi gets also copied, but becomes a NOT gate. So this is how you see here that a CNOT gate is a CNOT gate, just using the rules of the calculus. If you stick in a 0, it does nothing. If you stick in a 1, you get a NOT. So this is basically a CNOT gate being a CNOT gate. So you can start deriving these behaviors in the calculus itself and forget about the definitions of these spiders. That's all. Huh? Because that's a mistake. That's the one mistake I've got on my slide to make sure that people are following. I knew I had one. I know I have one mistake here, and it's always good if somebody finds it. So this should be a pi. You're right. This should be a pi.
First equation.
Just copying, just copying. The red dot gets copied through the green. And here the pi gets copied to the green. So that's this and this. Right? Everybody's okay with this? So CNOT gate is CNOT gate. Now we're going to go to some more sophisticated, because this is all baby stuff. Some more sophisticated stuff. So this is a Quantinuum paper from 2019, where people came up with like a methodology to basically simplify very complex quantum circuits. A strategy using the X calculus to simplify complicated quantum circuits. So I mean, these are all people based here in Cambridge. Ross was here yesterday. Oh no, he's doing a PhD in Oxford now. He's doing a PhD in Oxford now. They're here working with Ross. This is a Quantinuum paper. And they came up with like a strategy. So one thing I should say, there is no such thing, unfortunately, as a confluence theorem for Z. So a confluence theorem is a thing. Oh, what happened? Okay, man. Oh. So this is not full screen anymore, I think. What is this? something must have happened. Yeah, okay. Good again. Okay. Oh, too much time. Okay. So, right. Okay, yeah. So, come on. No, still. That. So, it turns out that to have a good strategy to simplify circuits, you have to learn to deal with this situation especially. So how would you start? What? How would you start dealing with this one? Turns out that this is the key, solving this one to simplifying circuits. That's a situation which basically gets you blocked. No, because that's only on a line. I mean, I told in advance you never lose this rule anyway. This only works on a line that you can alternate colors. They have to be on a single line. No, but this is not on a single line. It has 3 connections. So you're not allowed to do that. No, I mean, this is pretty much the only trick you ever need. But you have to be. So what do we have? Do you see a 2 cycle? I don't see a 2 cycle. And there is none. Do you see a 4 cycle? Kind of. Exactly. So you take these 2 together, and then you got a 4 cycle. Because this phase you can just pull out. So there's a 4 cycle sitting here. That's really the only trick you really have. Okay, let's look at that. So I'm doing it very explicit. So I fuse these greens together, then I unfuse them like that. I pull this alpha out, and you see there's really a square sitting there. I mean, you can immediately see it. You maybe don't have to do this, you know, but I'll just make it very explicit that you also can see the numbers very well. 1, 2, 3, 4, so there's a square sitting there. Okay, so we do our usual rule for squares. So whatever's connected to green, which is this alpha, and this 4 here, will be connected to red. Whatever's connected to red, that's the 3 and the 1 here, will be connected to green, and then we stick a little bit in the middle. That's really what we do here.
How you got that out?
Oh, it's unfusing. So suppose I can just fuse this, and this becomes an alpha alone. So I unfuse.
Okay.
I pull them out. You can do you can pull out such an alpha always, and that's why the rules without the phases for red and green stay valid if you got phases anyway, because you can just pull it out. So we're here, and now, okay, then so I'm just going to rewrite this a little bit, okay, to make it look nice there. So that's what we get. This is a really interesting thing what we just did, because you see here you get these you have these red dots which were blocking you from doing anything in the previous calculation. Suddenly you turn this into something with 2 green dots. I mean, you don't want to think about a thing like that anymore as a gate or anything like that. It's basically the result of some rewriting of this thing. But this is so much more useful because it's just green dots. So sticking it in, sticking it in here now. So see, these red dots were preventing you to do anything. Now you got this one, and you're done. You're pretty much done. Because these 2 can now fuse, they will vanish. These 2 CNOT gates, and you end up with this.
Can you kind of copy this green alpha?
No, you only can copy if it's a 0 or a pi. A basis vector. So this one you're not allowed to copy. Only 0 and pi. But anyway, so this trick allowed us to do something which seemed like impossible to do anything.
Can you show me the trick again? I don't think I followed. So this first equation, how did you get that?
This. So basically, these 2 green, they fuse together. And then I unfuse them. So this is just 2 green dots connected to, so you see, you got these 2 red dots, they're connected to green. It doesn't matter whether it's 2 greens or 1 green or whatever, because you can fuse them, unfuse them. I mean, I'm being pedantically explicit here to just make this square. I'm just being pedantically explicit here. Because you kind of can see it here. You got like a green dot, these 2 together, a red dot, and another green. So that's the square. And I'm just getting rid of the square using my rule. So you can even ignore this thing in the middle.
And how did that go
I just unfuse. I pull them apart because I can basically fuse them together, and then I just get this one. Yeah. So then, like I said, because now this whole chunk of stuff just becomes a green dot, and then you're done. You're done. So now this rule turns out is again general, so I'm going to write. So this is equal to that, and I'm again pulling this out for the reason that actually you can prove that something like this becomes something like this. Something like this becomes something like this. So a rewrite strategy for any circuits is whenever you see any of these things, you turn it in, you turn it into something like this, and you just got green dots, and everything commutes to each other. And that's how you can simplify things. I mean, it's quite a radical thing, but this kind of shows you how powerful this is. I mean, if you would stick with your C0 gate, you can't do anything. Here you've got this ability to turn basically something that's, something that's lots of red into just green. They call this phase gadgets. It has a name, phase gadgets, and they're very useful in like circuit reduction because everything commutes through everything, basically. Well, I mean, how you implement it is basically, I mean, this is a good, this is a good question actually. Like, as it turns out, for ion traps, this is kind of a primitive thing. They're very easy to implement. On other machines, you just have to do this. But the whole point is you got a very complex circuit, you use this rewrite strategy, you got a much simpler circuit, and then you implement it like that. But it's much simpler.
Is there always a kind of like minimal form? Like you start with
We don't know. We don't know yet. And I mean, I start to say something about like, there is a property which rewrite systems have, which is confluence, which means whatever path you take, you always end up in the same space. This is not true here. Confluence means like for a rewrite system in computer science, so they got a bunch of rules to rewrite something, that whatever you do, you always end up in the same place. That's not true here, and you've already seen in the calculation, sometimes we fuse, sometimes we unfuse, which are opposite directions. And you need both. There is no sort of one, the rules are not directed. You sometimes need them in both directions. And that typically means you don't have a confluence result in the sense that you'll always end up in the same place.
But this place is kind of like a dead end? Because of course I can apply a rewrite.
Yeah, like I mean, you can just go in circles here. Huh?
Yeah, but
A confluence system, all your equations will all be directed. You will only apply things in one direction, and whatever order you do, you will always end up in the same place. That's called confluence. And this is important for certain write systems, for computer programs and stuff like that. Like lambda calculus, that's like a formalism where you got results like confluence and things like that. So whatever order you use of rules, you always end up in the same place. You don't have that here. So you need some smart strategy. And this example I just gave you is a smart strategy, which seems to, but there is no theorem yet that this is the optimal thing to do. So this is all very much now in, research phase to basically use this stuff for practical applications. But that said, this is the best thing around now to simplify circuits. Quantum teleportation. Okay, remind again, 0, 0, 1, plus minus. So what we're going to do is now build a measurement, build a Bell basis for two systems. So the Bell basis is like a very important basis. It's 0, 0 plus 1, 1, 0, 0 minus 1, 1, 0, 1 plus 1, 0, 0, 1 minus 1, 0. It's basically a basis consisting of entangled states. So it's on two systems. Now the typical way people construct them is by, in practice, you take a C0 gate and you put some input vectors, and depending which input vectors you take, you get one of the different states. You can see this. I take the C0, a green here and a red there, and I can just get a cup. If I stick a pi there, the pi will be there. If I stick a pi there, the pi will be there. If I stick 2 pi's, you will have 2 pi's. So I mean, this shows you again this calculus in action for very simple baby things. Okay, teleportation. This was actually the first thing we came up with, like to do things diagrammatically. So you got Alice, you got Bob. Alice has a state, psi, and Alice and Bob share one of these cup states, an entangled state, and Alice wants to get this one to Bob. How do you do that? Yeah, exactly. You stick a cap. I mean, that's what it is. And of course, now if you're a quantum physicist, then you will say, but hey, wait a minute, you can't do this with certainty. You can't just do this. This will be part of a measurement, and you may obtain this, but not with certainty, only with a certain probability. What you typically do, or the only thing you can do is do a measurement against, for example, this basis, and then one of these 4 will occur. But you don't know in advance which of these 4 will happen. Okay? Okay. Okay, I already showed that. So this is just a little bit animation of what he does. Up. So this is what historically it was kind of interesting when I drew this picture for the first time, 2003, 2004. Independently, Luc Kaufman came up with the same picture in a paper in 2004. So he was in the air. He was in the air, so to say. And independently, when we came up with the first categorical quantum mechanics paper, John Byers had a paper too in 2004. But he had less. He basically was saying, we need to use these categories and blah, blah, blah. But he couldn't derive teleportation yet. Kaufman had teleportation, but he didn't have the categories. So we had both, so we won. Anyway, so here you got these two, and now it's very easy what you're going to do. So these are the results. These are part of your measurement. There may be a 0, there may be a pi there may be a 0 or a pi there, 4 possibilities. So this is what happens in your measurement. So in order for Bob now to get these states, he has to undo that. So you see, if there is 0 here, this will be undone by, well, nothing. If there's a pi there, it will be undone by this pi, and then all the red is gone. If there is a pi there, it will be undone by this pi, and then all the green is gone. So basically what you need in teleportation is you do need some communication from Alice to Bob saying, okay, I got this outcome, so please do that. And then you can basically move this state all the way down. So what is teleportation? Teleportation is not sending something instantly. Teleportation is sending some continuous data, which is a state, using 2 bits. That's what it does. But it's not going to violate relativity theory or anything like that. And that's where the communication comes in. So you got this communication. For old people like me, like this sort of an old telephone wire. You know? So you have to telephone, you have to call. Now you may say, a telephone wire is a wire. Why isn't this a wire in your picture? And why you do a curly wire? Okay, we're going to turn the curly wire into a wire in our pictures too soon. Because it would be stupid. So this is a quantum wire, so to say. This would be a classical wire. And we're going to now build pictures which have both classical and quantum wires together. And then, because this, I mean, again, this took us like, since this picture, it took us like 4 or 5 years to actually get this wire right. So this stuff all took a lot of time to come up with. It encodes the communication of, I had these measurement outcomes, can you please do this? Oh, I mean, at the moment, the curly wire is not really mad. It's just like saying, okay, somebody has to call. I'm going to turn it into mad later, and you'll see how you do that. I mean, of course, a classical wire and quantum wire won't be the same. So how will they be different? I mean, I have to explain. At the moment, we only have quantum wires, and soon we'll have the classical ones too.
One back to maybe slides where you had all the states, all the belt states we took out. Yes, here. Let's say I just want to understand the first equation. Why is the cap equivalent to this? I mean,
the green merge, the red merge. So you got a single dot on. So basically, you got a cap with just a green and a red dot, but a green dot on a cap or a red dot on a cap is all the same. So we just write this as identity.
But now you have both of them.
Oh, it doesn't matter, because I mean, it doesn't matter. When you got a wire and you've just got a dot on it, you just throw it away. Whether it's like this, whether it's like this, it doesn't matter. You first throw away one and then throw away the other. That's right. You first throw away one. It's like I mean, you can basically think of it as there's a red dot acting here and a green dot acting there, and they're just identities. So you just get rid of them. Okay, now I'm going to explain what measurement-based quantum computing is a little bit. So measurement quantum computing is like the kind of quantum computing where you don't apply a circuit to something, you just measure stuff, and you do nothing else. So this is like a simple primitive of measurement-based quantum computing. I think it was due to Simon Perdrix a long time ago. Not in this language, it is in the usual language. So we just saw teleportation. Basically what I want to do is like, I want to take this state and move it from this qubit to this qubit. Like, we were doing something similar here too. We had this state, and we want to move it from here to there. And we used one in the middle. Now we're going to try to do this without anything in the middle. So here, this is really just about wires, but if you want to do this without anything in the middle, you really need spiders. So here is an example how you can do it. So you got this state, I got a 0 state here, then I apply a C0 gate to both, and then I have this effect here, and you can see, basically this just means this becomes identity, and this thing goes there. Huh? Same principle as what we were doing just like. You can move this from here to there. Sounds like a very useless thing, but you can make it more interesting. If here I measure against a phase. Suppose I do a measurement here and possibly this phase occurs as an effect. What I get now this phase is going to move all the way there, because this is just identity. And now I've got alpha, psi, but with alpha applied to it. So I just applied a gate just by measuring. Never I had a phase gate here. There's no phase gate there. There's just this measurement against a certain angle, and in the process, it's as if I apply a phase gate to it. So this is the idea of measurement-based quantum computing. By picking your measurements in a certain way, you can actually apply stuff. That's the basic idea. And this has a lot of advantages, the fault tolerant, and like I said, everybody doing quantum photonics, all the companies, they're all doing this. They're not applying unities. They're all doing this. So now, just like in teleportation, we're going to do the correction. If you want to do an alpha, well, maybe you get alpha plus pi, which is orthogonal to alpha. We just stay orthogonal to alpha, and then you have to communicate and undo, like we did before in teleportation. So now you can, with certainty, apply an alpha gate like that. You need some classical flow here, but you can with certainty apply an alpha gate in this way. Now I'm going to show how you can apply any gate to a 1 qubit. I'm not going to do anything more. So suppose I've got my phi state here. Now I'm taking some plus states there. This thing is what people call a control Z gate. It's a kind of gate which is something like a C0 gate, a bit different. The way to write it down is like you got 2 green dots and an H in the middle. What does it mean? This horizontal line. This horizontal line means it doesn't matter whether I do this or this. It's the same. So I can basically have a fork, then an H in the middle, and then this, or I do it the other way around. It doesn't matter, it's all the same. That's basically why I can just draw it horizontally. So I've got this. So this is how you build what is called a cluster state. People call this thing a cluster state, like a bunch of stuff taken together by CZ gates. So I can just fuse them all together, so I get this thing. This is like a cluster state. This goes back to Hans Briegel and Rausendorf, 2000, 2001. Then they came up with this idea of computation. And now I want to apply an arbitrary 1 qubit gate to this psi. How am I going to do this? I'm going to use some measurements. Here are my measurements. I'm going to measure, I'm going to measure the first one. Okay, where are they? The first one against alpha, the second one against beta, the third one against gamma. This one I'm just doing a trivial measurement. Let's see what happens. I'm fusing everything together, so basically this just goes down, this just goes down, this just goes down, this just goes down. I get this, and now you see beta is between 2H. What does it mean? It becomes red. Here you got, this is just nothing, this is just a dot. Here you got 2 H's, they're going to annihilate each other. So I end up with this. And this is an arbitrary 1 qubit gate applied to psi using Euler decomposition. So, and I did this, I realized, I didn't do the corrections here, but you can do that. But I just realized this by doing one measurement on this one measurement on this one, and one measurement on this one. So just by measuring stuff, you're applying arbitrary quantum gates, and you can prove that this is universal, and you can do everything you want. So this is measurement-based quantum computing. Like I said, I mean, this is the sort of stuff that becomes really messy in Hilbert space if you want to do these computations. First, once a lot of entanglement starts to come into the picture, you can't do it anymore. And that's, like I said, this is what kind of the origin of ZX calculus, reasoning about this sort of stuff.
Is there some sort of paper where they explain this measurement-based computing with diagrams?
Oh yeah, I think Ross has a survey of measurement-based quantum computing or something like that in diagrams. I'm just wondering where this, what was this in my book? Oh, I can't remember. It appeared as a chapter in a book, but it's called something like a survey of measurement-based quantum computing in ZX. I mean, we do in our big book, we do all of this. We actually use cluster states to prove completeness even. So the original proof of completeness of stabilizer ZX was due to Miriam Bakkens, and that was done like using basically measurement-based quantum computing paradigm and universality thereof.
Yeah, so they prove like the universal like measurement-based, but then you kind of use it
To prove completeness, yeah.
Okay.
Yeah. So, but we got this in our big book, all of that. But like I said, Ross has a paper about it. I think a survey. Okay, now I think this is the coolest stuff. This is what I was talking about before with the telephone wire, you know. How do you represent classical versus quantum in these diagrams? And the reality is von Neumann already knew how to do that. He already knew how to do that. I mean, he didn't do diagrams, but he knew how to do classical versus quantum in diagrams, kind of. So whatever we've been writing before, like single wires, we're just now going to treat as classical. So this would be a classical circuit. Quantum will be everything double. Do you know why von Neumann already knew that? When von Neumann writes a density matrix, he takes a ket and a bra. He takes every state double and then sums over it. This doubling is the same as I'm doing here. So in a way, I'm going to density matrices. So the way you have to think about this is now classical probability and these density matrices. Density matrix, you write everything double. And that's the idea. That's the idea. It's the same. And it just could fail. It just couldn't work. I mean, it would be possible that this just doesn't work, but it works. It turns out it works. This is sound. This does exactly what you want it to do. And you'll see how simple everything becomes. Now, the one thing you have to be careful about is like, if there are phases, then the phases have to be like conjugate in the two pictures, and that's like having a ket and a bra in a density matrix. One is conjugate. Actually, what you got here, it's like a ket and a conjugate ket. You keep a ket, but you conjugate it, which is equivalent to taking a bra. But it's much simpler because you don't have to go in two directions. Everything goes in the same direction. So you got something and it's conjugate, rather than something and it's adjoint. And I think it's a big mistake that people have done from day one in quantum mechanics, to take something and it's adjoint rather than something and it's conjugate. It's much simpler. Everything is covariant. Everything moves in the same direction if you take a conjugate.
Yeah, actually a similar question like when you talked about teleportation, right? Like in general, like if you bring a gate from one leg to a different leg of maximum entangled state, it's going to pick up either a conjugate or a transpose.
Yeah. So the error and the correction, they will be adjoints from each other so that they eliminate each other, or transpose. Yeah. If they're polymetries, then it's the same. Yeah. I mean, I didn't do it here, but if you go to the Doda book, we represent all boxes like in an antisymmetric way, like as a trapezoid or something like that. And then so you can see that the adjoint is basically the flip. So you got a box which is like sort of a trapezoid. Conjugate is flipping like this. Adjoint is flipping like that. Transpose is rotation by 180 degrees. So you got these four symmetries, and they represent adjoint, conjugate, transpose, all of that. So I only talked about transpose here, like flipping upside down, just to keep things simple. But if you go to most, even in my kindergarten quantum mechanics paper, the very old one, you see these four options: transpose, conjugate, and adjoint. So there's really flip symmetries, the four things you get with your two mirrorings. That's really what you get. So transpose is 900. So adjoint really flips. Transpose is 180 degree rotation. conjugate is like that. So yeah, the thing is with the X calculus, it doesn't matter because all these spiders are self-adjoint, and so if there aren't any phases, the only thing which is there is like the negation of the phases if you conjugate. So they have a lot more symmetry than that, than standard linear maps. Anyway, keep things simple. We're just going to draw this as, in our book we use thick lines, but with chalk it's easy. It's not that easy to distinguish a thick from a thin line because it's a bit messy. So we just do double lines here. Double lines means quantum, single lines mean classical. So what is a measurement? A measurement is going from quantum to classical. That's a measurement. That's it. So our spiders are effectively measurements. So you got two in, which is, I mean, I put this a little bit apart so that you can see that they're two, but actually they're one quantum wire. This is a single quantum wire. This is a single classical wire. And a measurement is nothing else than a spider. So this is really like what I was talking about with von Neumann and Schrödinger, you know. I said like the failure of von Neumann quantum logic was they could never reconstruct the tensor product from this conceptual setup about measurement. What we just did is we construct measurement from a formalism simply based on tensor products. So it was built in there. It's built in there. So that's conceptually, I think, a very important insight, that you get this measurement structure out of your tensor notation. There's no diagonalization going on. There's no self-adjoint operators going on. There's nothing like that. It's just that. And of course, if I would take a red dot, it's a different measurement. They're complementary measurements, the red and the green. So this is the opposite. You've got something classical and then something quantum coming out. So this is like, I've got a bit 0. I encode it as a qubit ket 0. I've got a bit 1. I encode it as qubit 1, something like that. And so this is encoding. Now we can start. So I mean, concretely, what does this thing do? So this is a density matrix. Here you got a density matrix. If you stick the density matrix in there, you get this, which is a probability distribution. And this is the probability distribution of your two possible measurement outcomes. That's how you have to think about it. So you have to think of these wires, these single wires, as probability distributions flowing inside, which are the possible outcomes you can get in your measurement. What comes in are the density matrices. So
like in the previous picture, we were imagining wires.
So, I mean, do you know density matrices? Yeah, okay. So yeah, I mean, oh, sorry. So a density matrix, usually you would think of as an operator, as a map from, say, a qubit to a qubit. Here we're going to actually think of it as a state on two qubits. So, and that's again through you apply Choi-Jamalkovsky to a density matrix to make it like a covariant thing. It's an annoying thing about a density matrix that it has an input and an output while it's a state. It's wrong. And so we turn it into a state by taking this matrix and then represent it as an entangled state. And that's the difference between using a ket and a bra for a density matrix or a ket and a conjugate. That's really where this difference comes. So I'm writing this here as a matrix, but really I should write this as a state.
But somehow not every state on the tensor product.
Oh, no, of course not. They are special ones. They're the ones which arise from positive operators, of course. No, you're right. So they have a certain symmetry. They will have a certain symmetry.
Maybe my question is one quantum wire the same as two classical wires?
No. I mean, they are the same wires in the language, but conceptually they represent something different, of course. And there is an additional condition here, and that's what Lara was saying, that this must be the conjugate to this. And this symmetry, that this is the conjugate to this, will result in that not just any entangled state can be there, because they need this conjugate symmetry. They need this conjugate symmetry. And then you exactly get the ones which correspond to density matrices. I mean, you don't really, this is where I'm saying that translation is non-trivial. If you're used to usual, it's non-trivial, the translation, because you have to do things like this.
So it's two quantum wires, you have to keep them together.
It's a single quantum wire. It's a single quantum wire, and there is a condition on it that one is like the conjugate to the other. So it's not just like two wires. It's less than two wires, in a way.
You think that it's two wires, but then you're just only allowed to plug in certain inputs?
Yeah, I mean that's the same thing. You're only allowed to plug in like these things which have this sort of conjugate symmetry. Yeah. So that's the same as the positivity condition here. So you can translate the positivity condition here on a condition of symmetry, on a certain symmetry on these states. Yeah. But it's a different way of thinking than you're used.
Can't you kind of think of then applying some gates to one leg of this double quantum wire, and that would be like if I apply say U1 and U2.
So if you want to apply a unitary, then you would put here the unitary and there the conjugate.
Right. That's if I want to conjugate by it.
So if you would apply on the two wires two things separate, then this will be a pure operation. If they would be connected, that would be like a CP map, something mixed. So you got so a box here which has the symmetry you want and which applies to the two wires would be something like a CP map.
Right, but I would still kind of take a sum over the same Krauss operator.
Like yeah. So this would be like having Krauss operator. The sum on your Krauss operation will actually make a bridge. Diagrammatically will result in a bridge when you take a non-trivial sum on your Krauss operators. Yeah. So that's what I'm saying. This is a non-trivial translation. If somebody needs, it's not something you just come up with like that. But it makes things much easier. So like now, encoding, so here I maybe have a probability distribution on 0 and 1, and then I encode this as this diagonal matrix. That's what you're doing there. Okay, let's now do some trivial exercises. If I first encode in one basis, then I measure in the same basis, it's the same as doing nothing. Obviously. Okay, when I encode in one basis and I measure in the other basis, the input is totally disconnected from the output, which means they have nothing to do with each other. So this is already non-trivial. This is non-trivial. Whatever comes out here is randomness. So this thing is actually randomness. You know this from the physical intuition that it has to be randomness. So as a classical thing, relative to a measurement, this is randomness. You can all check this explicitly, of course. Okay, now the really cool stuff. So these measurements we had was quantum in, classical out. Now I can do measurements where I've got quantum in, quantum out, do projection postulate, and I get a classical outcome. That's this. Quantum in, quantum out, together with a measurement outcome. So this is a measurement which like a volume measurement, like the volume measurement described by a self-adjoint operator. Just to give you some, I mean, you can already see where the collapse is going on, because here you got quantum, and then you're forced into this classical wire. You see, I'm unfusing this now. It's as if there's for a little bit you live in a classical wire, and then you can encode it back in a quantum wire, and that's really the collapse. Collapse like matches up whatever this state is with whatever this outcome is. And to see this better, so we use two colors. Let's do this. We measure in green, then we measure in red, and then we measure in green again. I mean, if you know quantum physics, you know what's going to happen. People usually explain this with Stern-Gerlach operation, stuff like that. But these double wires, they vanish. Whether this is a quantum wire or not, doesn't matter. Two wires vanish, always. Now, what does that mean? That the first green measurement has nothing to do with the second green measurement. And that's because in the middle, you got this complementary measurement which completely changes the state into a state which is unbiased relative to this measurement. So these two are complete. Philosophers have written 1,000 books about this picture, effectively. Because that's really what it is. So you don't need spectral decomposition. You don't need all this mad stuff which you usually learn to do measurements. You do this with the spiders. And you can immediately see if you want to start proving things about completely positive maps, which is quite complicated, superoperators and stuff like that. This is going to be very easy. This stuff is going to be very easy. That's actually where this becomes super easy as compared to what you usually do. Okay. I mean, this is another example. This shows you that phases don't survive the passage to the classical world. So, okay. So what we're doing here is we got a measurement and we measure a phase, a state in a phase. We measure a state in a phase. This is actually two phases, conjugate. When I fuse them together, they vanish. So phases don't survive the passage to the classical world. So phases are something truly quantum. You can show this here. Right? Okay, the dodo. So this is teleportation. This is actually the full picture of teleportation here with classical communication. You can see the single wire versus thick wire. Yeah? So this is from the dodo book cover. So let's do this now. I mean, I promised we're going to get rid of this wire. Kind of already can guess what we're going to do. So I'm reminding you about these things. I showed them before, but we're going to use them upside down. So I put the picture upside down. So, okay. Okay, let's go here. So basically what we're going to do is, like, we've got this C0 gate here. That's how people do teleportation. And then you either get a 0 or a pi in this measurement. And that's what you have to correct there. And that's what we saw before. I'm sort of plugging this out to make it like how people usually describe teleportation using a C0 gate explicitly. Just doing the full thing now. Now, this has to be communicated to that. So here we got some sort of quantum thing. So basically we have to turn it into a classical thing using our notion of measurement. And then we use our notion of encoding. So this is how the squirrely wire is really a single wire, while the other wires were double wires. That's really how it happened. The one thing you shouldn't be confused about is, like, here you see green, there you see red, but it's just because the red spider copies the green bases. That's why there is this change in color. And now you can basically use all the rules we have. The only rule you have to basically, you can basically fuse these two red dots together. Then you get like and you can fuse this green together, and then you get two wires between green and red. They're going to vanish, and then the same is going to happen with these two wires. They're going to vanish, and that's how you prove that it works. You basically use, the only thing you use is some fusion and spiders and the two wires vanishing, nothing more. There's no squares here. There's no squares here if you do this. So okay, I think that I'm at the end. So everything I was talking about you can find explicitly in this paper from the course. This is the ZX. This is really like the set of ZX rules as we saw them today. Fusion of phases, color change. If I do the green fusion, I've got color change. I don't have to do red fusion. And then these things. So that's the calculus. That's what it is. I think, are we out of time? Pretty much, I think. What time is it? Pretty much out of time. So anyway, in the kids' book, if you're going to buy it, it's very cheap. You can use just these rules and nothing else to prove quantum non-locality GHZ style. I mean, I can just, so basically, these are, do people know the GHZ proof of non-locality a little bit? So yeah, you got these 4 scenarios of measurement situations. You got 4 scenarios of, so you got a GHZ state here at the bottom, then you do different measurements on each, and this is a choice which you make of either doing this 90 phase or not. That's really what it boils down to. So you got these 4 scenarios. You just fuse all these red things together, and then you can use the commutation of green and red, and basically all these phases are just going to add up there to 180. Then you got this picture. This is the picture of a local hidden variable theory, if you know what this is. Basically, we're now saying that each of these measurements has some predefined outcome. In each of the scenarios, these are the predefined outcomes. You copy them to the different scenarios, and now you see 2 wires between red and green. They're going to vanish. And basically, here you get 0, there you get 180, they're incompatible, and quantum mechanics no local. Okay, this was very quick, but this is really how it works. So you get the full proof in these pictures. Right. So there is this book you can buy, it's cheap. There's this book you can buy, not so cheap. It's not too expensive, it's CUP. I think it's £60 or something, which for 900 pages hardbound is not too bad, you know. It's not too bad. This one's like £10 or something in color, but that's because we sell it at loss. Why would you sell at profit if you can sell at loss, you know? Anyway, I think that's it. I think I've got nothing else. Yeah, that's it. Thank you. Yeah.
Slightly real-world, slightly inaccurate system. So in fact, the green basis is actually a 91 degrees. I think the rules are going to get very complicated. Do you think this system is useful?
Well, I mean, it is used for universal computation, and in universal computation you use ugly angles. Well, you got the theorem, the completest theorem says that any equation you can prove in Hilbert space, you can prove here, anyway. And some... An equation that you can prove. There's so much literature on this stuff. So people are using this to do really, really complex stuff. Oh, la 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 la. From the top of my head. I mean, one example is, for example, this is equal to just a red dot with 180. This you can reduce to just one dot, a red dot of 180. That's an equation that you do. I mean, typically when you find this in a textbook, you don't see this as maths. You find this with a lot of words. People, all the stuff which happened on top, which is a classical, which is actually a parity calculation. The top is a parity computation. You compute the parity over all possible outcomes. That's something that people would do with words. They wouldn't sort of, it's not something people would typically formalize even. They would say this in words in most textbooks. So here you have a fully comprehensive language where the whole argument is just a picture. So that's an additional bonus to having this classical and quantum together. I mean, if you go to some of these measurement-based computations, you say the implementation of a, I don't know, whatever unitary, it would be super complicated. And it would be, and so people actually now have introduced notations on top of notation here. Like, for example, when you got a lot of repetition of stuff, which you typically will have in something like a measurement-based computation, there is notation to say, okay, this repeats itself 100 times. And then you do, like, people have sort of meta-notations now on top of this. But if you go to a paper of PsyQuantum, for example, the company of PsyQuantum, it will be packed with these diagrams to compute like error correction systems and stuff like that. There's quite a few softwares available now. There's something which is called PyZX, I think. Pi like from Python, Pi and then ZX. And I think there is something called now news, which is ZX Live. There used to be an old system I paid a lot of money for, Quantumatic, but the lack of people being software engineers made it completely fail because they didn't really know how to write a proper piece of software, and in the end became a complete mess. This is the good thing about working in industry. You can actually hire software engineers, which is very hard in the academia.
The trick you did where you had the three measurements and then the one in the middle of the tangle, is that what you, here you have like two legs, the two quantum wires, do they always tangle neighboring red and green?
They will just fuse together. I mean, I didn't.
Like, think it's nothing. If you have a red green node and a green node and two wires between them.
Be careful. This is a double red node. So these two wires. Okay, no, that's a double red node. So if you unfold this, you will see you don't have that.
Okay. So
here you need squares. Here you've got squares actually. This is a place where you actually need to reduce squares.
So then you work where you create kind of verify where you have all the properties somehow encoded in this, and then you connect it to the circuit and show whether it fully verify whether it does what it's supposed to do. Like, can you do full verification for this?
Well, I mean, initially, and there was I remember Samson, when we just came up with this categorical quantum mechanics, he said, oh, this is a system to verify quantum programs. We can verify quantum teleportation. And then the people in quantum computing say, we don't need you to verify quantum teleportation because we know it works. And then we don't need your stuff. And that actually, that lasted for many years, that people say, okay, they're doing very complicated stuff to do something trivial. And it takes a while to get rid of that sort of label, really. I mean, exactly. That's. I mean, in a way, you do calculation and verification at the same time.
So it's not too separate. You don't have to verify circuits.
You could do, but we're only barely coming into the domain where for quantum computing we would need verification. Really, it's. I mean, there's still a lot of paper coming out with Hilbert spaces, you know, which means we're still in the. I mean, for me, Hilbert space is like a list of complex numbers, just like programming with zeros and ones is just a list of zeros and ones. So with Hilbert space, we're still at the sort of, Not even assembly level, not even. I mean, people have used this also as some sort of intermediate language, language between like. So initially we were selling this stuff as high-level language for quantum computing. It's mostly used now as a low-level language to really explicitly do error correction and circuit simplification, which is also low-level. So you never know with these things where they end up. But at the same time, it's still a high-level language too, I would say. It's a little bit both. Thank you.